to record. So we're recording now because, I forget these things. But I was specifically interested in, especially as you were doing matrix stuff from 3.1 using Maple. So what are some like things that you need to remember when you're using Maple and doing this stuff in Maple? I mean, nothing too big. I mean, not a big deal. What are some things that, oh yeah, I got to remember to do that whenever I'm doing this stuff?
Gotta remember to use the linear algebra thing.
With linear algebra. So we have a kind of a laundry list of things that are with our libraries that we kind of want to load. With DE tools, with plots. The student numerical analysis, that one, we only use it for a single equation Euler's method. And we don't do that much. But with linear algebra, that's another one that we're going to add to the mix. There's one more that we're going to get to later on in the course, one more with. But if you've got those loaded, you can pretty much do anything that we want to have for the course. What else in Maple is important? Matt, you and Bryce stumbled upon together when I happened to be in the room, just matrix arithmetic in Maple. What did you notice about multiplying matrices?
That you can use space, so like A space B is the same as multiplying them together.
Yep, so you don't even have to put a multiplication symbol, which by the way would be the period, not the shift 8 multiplication symbol. So as long as you remember to leave a space, make room for multiplication, then you could actually multiply two matrices that way. And they don't have to be named. You can literally have matrix entered and then space and then matrix entered. And then you could do it that way. That works. So that's important. In question number 2, you were asked to explain whether things were linear, explain whether things were autonomous. I hope nobody had run into any trouble with those. Those are concepts that just keep coming up. We're going to be seeing those to the end of the course. You ran into it in the last exam. And then I said to rewrite it in matrix form. So what was the sneaky Steve catch for question number 2, part C?
You like flip the x and y in the equations?
Yeah, because if we're
Just
writing the
order.
equations like dx dt, it doesn't matter whether it's 2, whatever it was, 3 pi y minus 0.3x or the other way around, because addition is commutative in normal equation land. But in matrix land, that coefficient matrix, each one of those columns represents the coefficients for a particular variable, and you can't mix and match. It has to be all these are the x coefficients and these are the y coefficients. Because when we multiply that matrix by xy over here, then that makes a big difference, or xy over here, I guess. That makes a big difference. So knowing that you've got to put those equations in order, and if you're going to have dx dt be the first row and dy dt be the second row, you got to remember which is which, and that's got to be reflected in your choice of variables in the matrix over there as well. This is it's matrix hygiene, but it's important when you're entering stuff. You can totally mess up a problem just by having 2 numbers impose or switched this way or switched this way in a matrix. It's completely different if you do that. So speaking of number 2, did anybody have any trouble with making a vector field or a phase portrait for that one? What do you have to have loaded to make a vector field?
With plots.
With plots. Because you can't make a field plot unless you have the with plots loaded. And yes, a vector field is not the same thing as a DE plot. Because a DE plot, all it tells you is direction. It is literally a direction field. That's all that it tells you. It doesn't tell you the magnitude of the vector, right? So if I want a vector field, that means I want to see the magnitude difference, And so for that one, you could really tell the difference in the length of the arrows depending on where you're looking on the XY plane. Let's see. Did anybody tackle number 3? Anybody try number 3? No?
Yeah.
You guys did?
Yeah.
Cool. Can you share what you got? What you came up with? So number 3 was, it's like the only time we're really going to do it for reals, a system of 3 differential equations that you had to turn into a matrix. Let's see if it works. Dun, dun, dun.
So we just kind of did the same as what for the 2x2 for the last one, where we kind of just went along the line, just kind of plugged it in.
And you got to make sure that they line up vertically so that all the p coefficients line up. That's why that bottom row has a 0 first, because there's no p in that row.
0p here.
Yeah, I mean, you could say it that way, absolutely. As a matter of fact, sometimes in the process of converting from, standard differential equation form to matrix differential equation form, writing those zeroed out coefficients can be really helpful. And so, sure enough, that does work, because when we multiply those 2 matrices, the first row gets multiplied by the column, the second row gets multiplied by the column, and the third row gets multiplied by the column. And so you'd reproduce all 3 of those equations just like that. Well done. Nice. Did anybody try number 7? I thought I'd have fun with that one.
Yeah, I also did that one.
Did you? Okay, so anybody else want to share and show us what you got?
Oh, we also did 7.
Cool. You want to share?
Yep. Just give me 1 second.
Austin, are you trying to talk? It looked like you were trying to talk, and I don't think we're hearing you. Or were you talking to somebody else?
I was just raising my hand like, oh yeah, we did that. Then I realized I was muted, so
Got it. No problem. No worries. So walk us through. What'd you do here, Matt?
So first, for 7a, we were supposed to name it, or we were supposed to make one up. So we just made one up, named it C. We then took the inverse, and then we named the inverse E, and then took the inverse of the inverse.
Hey.
E, and then we took the inverse of the inverse's inverse.
Can you look closely at P and tell me if that looks familiar?
Yeah, it's the same as C.
And then you take its inverse, and predictably.
And then it was the same. And so that's actually what we said back down for F, is that continuing to take the inverse of other inverses will just revert the matrix back to the original numbers.
So thank you. That's terrific. By the way, you could also string this along and make it one big code. You could say matrix inverse of the 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 matrix. And so you could add as many matrix inverse ofs out front and just kind of keep adding an extra parentheses, and you could do it that way too. So how does this make sense? You take the matrix inverse once, you get some crazy matrix. You take its inverse, and you're back to where you started. How does that make sense?
Because you're like canceling out the inverse. You're using the inverse with the inverse, so it kind of just cancels out.
So the matrix inverse operator follows kind of the same rules as all of the operators that you've learned up to this point. It's pattern-wise very similar to derivative and integral, addition and subtraction, multiplication, division. They undo each other, right? So f of x, f inverse of x. It really is just an inverse operator. And this is why you can't have a matrix, a matrix that doesn't have an inverse can't be inverted, because it can't complete the loop. It can't go back to itself. So a matrix that has an inverse can be then re-inverted back to itself. So in a way, it's very much like functions when you learned about functions. A function that has an inverse should be able to be re-inverted back to itself. So f inverse of f inverse, that kind of thing. So again, just for fun. I just wanted you to see how matrix inverse works. Anybody try another one? Any of the other ones? So 3, or we did 3. So 4, 5, or 6? Any of those? I know some groups didn't have time for that, but did anybody tackle 4, 5, or 6?
Did 4.
You did 4? So what can you tell us about 4? What did you do for number 4?
We just set it up into the scalar form, like took it out of the matrix form, put it in the scalar form, and then used a desolve with the initial condition,
Yeah.
which we also had to put in like a scalar form kind of thing.
Yep. And it's important to note, nowhere on there does it say you must do this by hand. And by this point in time, you should be pretty aware of the fact that when I want you to do something by hand, I'll explicitly say do it by hand. And that means if I don't say do it by hand, you can use Maple, right? You can just do it in Maple. And so show us how it turned out.
So yeah, we just turned it into the scalar form and did the desolve there, which we got that, which is in its scalar form, but then just turn it back into a matrix form.
Cool. And that was what I was going to ask at the very end, because we didn't specify what our dependent variables were. You chose dx dt and dy dt, but really that was just so you could communicate with Maple. In the end, it didn't matter whether it was x and y and t. All that mattered, well, in this case, t is defined by the problem, but x and y, those are just window dressing, right? The dependent variables could literally be anything, because the problem that I gave you doesn't specify what the dependent variables are. It just says, here's the coefficient matrix, here's your initial condition in terms of a matrix, give me the solution, and what you've given is the particular solution in matrix form. Perfect answer. So is everybody clear on the distinction? They had to invent dependent variables because there weren't any specified. And so they went, we'll just call them dx dt and dy dt. They could have called them dp dt and dq dt. They could have called them whatever they wanted to. But in the end, it doesn't matter because the answer is going to be in matrix form anyways. So thank you very much. Excellent work. As you can imagine, number 5 is all about practicing turning our second order into a system of first order, and then being able to find solutions from there. And then number 6 is again more of a kind of a theoretical one. Imagine you have a matrix, a coefficient matrix, and it says play around with the determinant and stuff. It's mostly just kind of stretching our legs. I don't mind jumping past that. What I do want to take a look at is section 3.2. And rather than do the classwork exercises as written, what I'm going to do is I'm going to show you guys another problem. And so I'm going to share my screen with you. And this has a fixed problem. Here's a system of 2 differential equations with the dependent and the independent variables defined. What I would like you to do is solve this, but I don't want you to use Maple. So desolve is off the table. What I want you to do is go through the process of solving this using the eigenvalue, eigenvector method from 3.2. And so I'm going to put you guys back in your breakout rooms. Oh, I was going to. Yeah, I'm going to. And then I'm going to have you guys work on this. But what I want you to do is have one person kind of drive the bus writing this out or typing it. If you want to type it, that's fine. The other person, I want you to refer to the notes to make sure that you're doing each step and kind of following each step. So have one person be in charge of driving the bus, the other person be typing or writing. And then I'm going to have you, once you've solved it, once you've got a solution and you think you're right, I'm going to have you switch roles, and the other person is then going to check it by doing solution using Maple. Does that make sense? Okay. So I'm going to open up the rooms, and John, I think I'm going to have to toss you into the room once things get in there. So hold on. And John, I'm going to put you in. Oh, I don't know. So we'll give you a couple minutes. I'll be around if you need anything.
Let me see if oh, there's my face.
There's Snapchat.
So it's a little bit delayed. I wonder if I can I want to turn it sideways.
Mhm.
Dang it. That doesn't work.
That's kind of cool. Is it because it's an iPhone?
Yeah, I can. It's an iPhone and a Mac, so you can spray. I'm trying to. I was wondering if I can put it, kind of balance it here, and then get a bit of a
look
dot
at
cam
that.
going.
Oh crap,
Yeah.
man.
That's
Awesome.
rocking. Of course, you have to. Can you rotate the phone?
I gotta we'll figure. This is something that needs some work.
That's pretty cool. Yeah, rotate the phone. I think you got it. Look at that.
It won't let me turn it sideways or anything. So I don't know what I'm supposed to do there. You know, I can hold it for a little bit. All right, White. What's step one?
Okay, so step one. Where are we looking at? Page 25. Okay. So all right, so remember right from the notes we gotta get the what is it, the tournament, which would be what is it? Well actually we should probably put it in matrix form before we do anything. So hang on, what were the what was the thing again? I can't see it.
Oh, they're up there. So my bad.
Okay, so x plus 4y, so it'd be 1, 4, 1, and 1.
I'm gonna see if I can move some things around real quick. Kind of try that. How does that work? Can you see that sort of?
Yeah,
Better?
that works good.
Unfortunately, bottles aren't like working like that.
Nah.
We'll get a better system later. All right, what were you saying, Wyatt?
It'd be like 1, 4, and then on the top row, and then like 1, 1 on the bottom row.
No, 1, 4.
Oh, 1, 4.
Well,
I
not
see.
comma, but first element 1.
Well,
Second
1,
element
4, and then 1, 1.
Mhm.
I guess I could have like thought for 3 seconds and then figured that one out. This would be
Like
X,
Y.
Y. Beautiful. Now
Okay.
what?
Okay, now that we have it.
By the way, I shared I think a really cool looking, super simple .cam using a couple of cans of soup that might be interesting for you. So check it out. Isn't that creative?
Pretty good.
It seems
That's
to
good.
work. So
I might use that. I'll get a little contraption up
cool.
within due time. I might like get a fishing rod and just kind of
There you go.
put it in a plastic
gonna-
bag. Maybe.
I'm gonna hop in the next group here.
Okay.
All right.
So our V1 is going to be it's going to be 1/2 and 1.
Yep.
Or
No, 1/2 and wait, what?
1 and 1/2.
Yeah,
Or if you prefer, you could do
1/2 and 1.
2 for X and 1 for Y.
True.
Does that make sense? So if you were really averse to using fractions, you'd say, well, if X is 2, then Y is 1. And that would be just as easy. So usually for eigenvectors, it's kind of considered to be proper form for at least one of the numbers to be a 1. And it's, if possible, to avoid fractions, but it's completely user defined. So if you're okay with that 1, 1/2, that works fine.
Okay.
Mhm.
Or 2.
Good to know.
You guys are doing good.
Thanks.
Yeah, looks good.
Now we got to do the other lambda.
Which is what? What was the other one?
So we're going to record again because I keep forgetting. Here we are in Maple figuring out how to use the eigenvectors command. Maple says if you ask it eigenvectors for a matrix, it gives you an output. The first thing before the comma, that's telling you what your eigenvalues are. And then the second thing after the comma is actually telling you both the eigenvectors, but in a very particular way. So the eigenvector that's associated with that value is -2 and 1. It's vertical, not horizontal. And so it's got to be -2, and then the other number is 1. And so typing it this way, it's just as easy. If I wanted to, I could go over here in matrix land and say insert a shape. I want a column vector. I just want 1. 2 rows, 1. There we go. I could do it this way. Say it's -2, 1. That's my first eigenvector. And my second eigenvector, I'm going to be lazy and copy and paste, is +2, 1.
We got like half of that for each eigenvector. We did them by hand. Like we got -1/2 and 1.
So
And
here's
1
the
and-
question. Is this eigenvector right here, how does that compare to if I put a 1 there for the top number? What does the bottom number have to be in order to be pointed in the same direction? Remember, this first one is saying go right 2, up 1. So if I go right 1, what does this number have to be?
So that would be 1/2.
And that is a 100% equivalent vector direction. Now you might say, but it's a different vector. Well, it's pointed in the same direction, and that's all that matters. So whether you go right 2, up 1, or you go right 1, up 1/2, you're pointed along that same line. So this is the weirdness of the eigenvector. All we care about is the direction. The eigenvalue tells me the magnitude, how quickly things are moving in that direction. The eigenvector is just pointing you, go that way, right? And whether you hold your arm like this or you hold your arm like this, the direction is the same, right? It's pointed in the same direction. So up here, what's an equivalent matrix for this one? What's another way I could write that one?
-1 and 1/2.
Okay. Give me another one. How about if the first one is 1?
-1/2.
Does that work? Is right 1, down 1/2 the same as going left 1, up 1/2? Remember, it just needs to point along the same line. And whether you're pointed this way or that way, it's the same line. The direction matters, not how long that arrow is. So this is where it gets a little strange, right? All of these vectors are equivalent. As a matter of fact, if you typed this into your Maple, eigenvectors 1, 4, 1, 1, if you type that in, you might get these two numbers in the opposite order. You might get these vectors correspondingly in the opposite order. Sometimes when you solve by hand, you might get this when you solve it by hand, but have to realize that it's the same as this when you're checking it in Maple, right? So all we care about is that, are they equivalent? Are they pointing along the same line? And in this case, they are. How about this? What if I told you the first number is 10? What's the bottom number have to be?
-5.
-5. There's only one option for the bottom number. Don't get me wrong. If I choose the top one to be 10, the bottom one has to be -5. If I choose the top one to be -10, then the bottom one has to be +5. That's it. There's no other option there. So these are all equivalent vectors on the phase plane because they're all pointed along the same direction. It's a little strange, but that's the way eigenvectors work. Now you might think, oh, that one's more attractive to me than this one is. Fine, you can use that if you want. You will get the equivalent answer. It will work out just fine. So once we have our eigenvalues and our eigenvectors, how do we put this information together here? I'm just going to erase these guys. If I have the eigenvalues and the eigenvectors, then what do? How do I turn that information into a general solution? This is the big finish of 3.6. This is the big punchline that makes it all worthwhile.
So you would take E and raise it to the -t times the first eigenvector for the first one?
That's going to give me a straight line solution. So if
Oh,
I just wanted the straight line, if I just wanted the straight line solution, then I could say E, and I know it's not the proper E, I can go E to the power -1 times t times this first eigenvector. And this, my friends, that is the first straight line solution. So you could call that Y1. That is straight line solution number 1. And if I want the other straight line solution, it's not going to like me very much for doing this, but I don't care. I can just change this from -1 times t to what my second eigenvalue was, which is 3. Stick a 3 in front of it, and then replace that second, or replace that eigenvector, the first one. And now I have my second straight line solution. And again, you look at that and you think, what's that telling me? That's telling me we have exponential decay headed towards the origin along the line that is go to the left 2 and up 1. That line that goes through the origin, you're going to see it decay towards the origin because it's a negative eigenvalue. This one's a positive eigenvalue, which means it's going to be going away from the origin along the line that is go right 2, up 1. And so if you can imagine that line, it's going to be going away from the origin. And again, I'm doing all this without seeing any phase plane, without drawing a picture of the phase plane. I know I've got 2 straight line solutions. One of them is in this direction, and it's going to be running away from the origin. The other one is in this direction, and it's going to be running towards the origin because it's a negative eigenvalue. And if I want my general solution, all I need to do is put these 2 turkeys together. And I say, okay, one big solution, and I'm not in equation form, but you get it, K1 times my first or my first straight line solution plus K2 times my second straight line solution, which is this guy right here. I don't need all that. And it's not pretty, but that is the matrix form of, oh, I don't need all this either. It's not pretty, but that is the matrix form of my solution for this system. Now, if you remember, the system was the equations dx dt equals x plus 4y and all that stuff. I can still pop into Maple and say, hey, can you show me a DE plot of those equations? Where the first one was, I don't know, what is it, x plus 4y? So x of t plus 4. Why am I doing this? I could do this probably faster in a field plot. So this is just going to be x plus 4y, comma, x plus y. And we'll do, I don't know, x goes from -5 to 5, and y goes from -5 to 5. What did I do? Oh, y goes from, there we go. Boop. So on my field plot, it's kind of hard to spot them, but you can see there appears to be a line through the origin that kind of runs this way. And above it, the curves kind of bend up and away, and below it, the curves bend kind of down and away. There's a straight line solution that kind of passes through there that's got a negative slope. That's my first straight line solution. If I go right 2, down 1, that's the line that I see, the straight line solution. The other one is kind of running this way. And if I draw a line straight out this way, if I go right 2, up 1, there's my straight line solution, my second straight line solution running through there. And you can see along that straight line solution, everything's headed away from the origin. The first straight line solution, everything's headed towards the origin, right? Everything's decaying towards the origin. So field plot lets you see it quick. A DE plot lets you put in those initial conditions. So this is stunned silence, but I want to make sure that what we started with was finding the eigenvectors and the eigenvalues and eigenvectors for that coefficient matrix. Everything we need to know about the phase plane is encoded in those 4 numbers. It gives us eigenvalues, eigenvectors. From that, we have our straight line solutions, and from the straight line solutions, we have our general solution. How we feel about that? So-so? Yeah. It's muted silence from the crowd. So I just want to make sure the process is fairly straightforward. You just have to practice it a little bit. Finding the eigenvalues, finding those eigenvectors takes practice. So for those of you who were running it, doing it by hand or typing stuff in, I popped in and I saw kind of progress. It looks like you've got the process down. You have to do it a couple of times before it starts to click. Now, you can always check it on Maple, but please know, I'm going to ask you to show me the work, the step-by-step for how you come to know the eigenvalues and the eigenvectors without just saying, hey, Maple, what are the eigenvectors for this, right? You can always do that, but I want evidence that you understand the process behind it. Does that make sense? And the good news is, if you understand the process behind it, then you can answer more interesting, complicated questions. For example, take a look at number 3 on the classwork for 3.2. It says we're given a coefficient matrix for a system of 2 linear differential equations. Unfortunately, one of the numbers was smudged. Wah, wah. So we stick an X in its place. So you've got 1, 2, 3 of the numbers, but you don't have the 4th in the coefficient matrix. And we're told that one of the eigenvalues for this system is 2. So what do we do? And that's where I'm going to leave it for tonight. We're going to get out a little bit early, but each one of your groups, just that one problem, you're going to try to solve it, come up with a solution that's more than just here's the answer, here's what X equals. I want you to be able to show me what X equals and to prove how you know that X must be that. And you're going to send me that solution before, I don't know, Saturday night, Sunday, somewhere in there, sometime this weekend, right? It's not going to take you long, but I want you to think about it. In the meantime, you're going to have to practice a little bit with the process for finding eigenvalues and eigenvectors. And this is a good problem to kind of force you to have to practice a little bit. So does that make sense?
Are we submitting like individual or as teams?
As a team, yeah.
Okay.
Each team, just send me something. You can do it in Maple. You can do it by hand if you want to do it by hand. That's fine. I don't care. Just send it to me. Send me an email. This is just a short, quick little homework assignment, 10,
So
20 points.
We're getting points? Okay, cool.
Yeah. Oh, it's definitely worth points. It's worth 1,000 points if you don't do it, but 20 points if you do. So. Sound good? And hey, we're getting out 10 minutes early, just so you can have a little bit of relaxation. Yeah. Matt, you seem confused. Don't be confused. I'm sure we'll have more time to do math later. Matt's like, I'm done already. Are you kidding? Steven, it's past 7:30. You must be ready to take a nap at this point, right?
I am, yes.
Okay. Get out of here. Just shoot me an email. I'll probably send a little reminder poke on Friday if I don't hear from you guys before then. But otherwise, have a good weekend. Have a safe holiday. And I will see you all on Monday. Toodaloo.